आज हम समझेंगे. Welcome to today's explainer, where we are going to completely demystify C++ bubble sort, and we're doing this in a highly animated true samjhao ke style. If you've ever stared at sorting algorithms and felt, well, kind of intimidated by all that syntax, you are absolutely in the right place. We're going to visually break down exactly how this code actually works behind the scenes. By the end of this, you won't just be reading code, you're going to literally see the array organizing itself right in your mind's eye. So, let's get into it.
Okay, let's dive into this. Right here is our messy, raw, totally unsorted array. 5, 3, 7, 3, 88, 33, and 67. This is exactly how the data is initialized right inside the main function of our source code. Now, when you or I look at this list, our human brains just immediately spot the outliers, right? We instantly recognize that massive 88 sitting right there in the middle of the pack. It's totally out of place. But a computer, it doesn't process information like we do. To the machine, this is just a sequential block of memory. It literally cannot see the whole picture at once.
So that brings us to the central conflict of our explainer today. How do we actually sort this? Think about it. How do we take our intuitive, human logic, that natural desire to organize numbers from smallest to largest, and translate that into a rigid, step-by-step set of instructions that a computer can execute flawlessly? The machine needs rules, guys. It needs a foolproof methodology to handle these random numbers without getting confused, regardless of how chaotic that initial array is.
And the answer we're exploring today is the classic bubble sort. Honestly, it's one of the most foundational algorithms in all of computer science. And the definition? It's just elegant in its simplicity. It's a method that compares adjacent elements, meaning, two numbers sitting right next to each other, and swaps them if they're in the wrong order. Now, why the name bubble sort? Well, picture a glass of soda. Just like those little carbonation bubbles naturally rise to the surface, as this algorithm runs, the largest numbers, like our 88 or 67, will literally bubble their way up to the very back of the line.
Step 1. Loops and conditions. Let's jump right into the core mechanics of the C++ code and look at the logic required to systematically sweep through all this data. To make this whole bubbling action happen, the computer needs a way to repeatedly check every single number. It can't just glance at the array once, right? I mean, a single pass might move the absolute biggest number to the end, but the rest of the array? It could still be a complete jumbled mess. So, inside our bubble sort function, we achieve this repetition using nested loops. We've got two for loops working together here. The outer loop, using the variable I, acts as our main counter. It runs from 0 up to n, basically making sure we do enough passes to sort every single item. But the real heavy lifting? That happens in the inner loop, using the variable j. Running from 0 to n minus I minus 1, this inner loop is what actually travels across the array elements during each pass, physically carrying that bubble along.
Now, what's really interesting about this slide is this exact if condition. If array rj is greater than array rj plus 1. Seriously, this single line of C++ is the beating heart of the entire algorithm. Imagine the computer holding a tiny magnifying glass that can only fit exactly 2 adjacent slots of the array at a time. It looks at the current slot and the slot immediately to its right. And it just asks one super simple question. Is the number on the left strictly greater than the number on the right? If the answer is yes, boom, they're out of order.
Let's visualize that very first comparison right at the start of our array. Before the action, our left value is 5, and the right value is 3. The computer runs that if condition we just talked about. Is 5 greater than 3? Yes, absolutely. Because that evaluates to true, the code triggers our core action, a swap. After the action, the 3 is now safely sitting on the left, and the 5 has moved to the right. The heavier number is officially beginning its journey, bubbling its way to the end.
Step 2. The swapping process. So how exactly does a computer swap two values without causing a massive data disaster? Let's check out the exact syntax.
Because here's the thing, if you don't do this carefully in C++, you risk completely overwriting data and permanently losing elements from your array. Nobody wants that. So, to prevent data loss, we need this critical line of code. Int temp equals rj plus 1. We essentially have to create a temporary holding space in the computer's memory. It's kind of like having a glass of milk and a glass of juice, and you want to swap the glasses. You can't just pour the milk into the juice glass without making a huge mess, right? You absolutely need a third, temporary glass. And that is exactly what this temp integer does for us.
So, the crucial takeaway here is this 3-step sequential choreography inside our if block. Step 1, we pour the juice into the empty glass, meaning we take the right side value and store it safely in temp. Step 2, we pour the milk into the now empty juice glass. We take the left side value and overwrite the right side. Now, at this exact millisecond, both slots hold the left value. But don't panic, that's totally okay because of step 3. We take our safely stored original right side value out of temp and pour it right back into the left side slot. And just like that, the swap is perfectly complete.
And this brilliantly illustrates how the code handles our massive numbers deeper in the array. When that inner loop finally reaches our giant 88 on the left and the smaller 33 on the right, the exact same three-step logic kicks in. The 88 gets moved into the right spot, successfully pushing it further along. Meanwhile, the 33 is rescued via our trusty temp variable and securely placed into the spot on the left. The 88 is officially bubbling up. Step 3. Let's see the output. Time to move from the sorting function to actually displaying our hard work.
Okay, so those nested loops will just continue to churn, repeating these comparisons and swaps until absolutely no more swaps are needed. But doing all this sorting in the background memory, that's really only half the battle. If we can't see it, the work is basically invisible to us. Back in our source code, right below the sorting logic, we have a separate function dedicated entirely to showing us the results, void display. This function is beautifully simple. It just takes the newly organized array and its size as parameters. Its sole job is to iterate through this pristine, sorted memory block and print it out to the screen so we can verify it. But before it just spits out a giant wall of numbers, it uses a standard C++ output statement, cout, then the sorted array is. This gives the user some much-needed, clear context. Right after this specific line of code executes, the display function fires up its own single for loop to systematically pull each individual number out of the array and print it alongside a blank space. This creates a really clean, readable row of data.
And here is the grand finale, our beautifully sorted array. 3, 3, 5, 7, 33, 67, and 88. Just look at how the code successfully handled everything. It recognized that 5, even though it started at the very beginning, actually belongs somewhere in the middle. It safely managed our duplicate numbers, keeping both 3s perfectly organized side by side. And true to the algorithm's name, our massive 88 bubbled all the way from the middle of the pack to take its rightful place at the absolute end. How cool is that?
We've essentially taken a messy, chaotic list and used the sheer logic of nested loops, temporary variables, and adjacent comparisons to create perfect order. You now have a rock-solid visual grasp of exactly how a bubble sort operates under the hood. But before we wrap up this explainer, I want to leave you with a final thought to ponder. Bubble sort is undeniably easy to read, write, and visualize. But is it the absolute fastest way to sort data? Think about it. What happens if that array has 1 million numbers instead of just 7? The answer to that question opens the door to an entirely new world of advanced algorithms, and I highly encourage you to keep exploring.